Hello friends, welcome to my channel. We are going to discuss here about the formal definition of limits. So, suppose y equal to fx is defined on open intervals b, comma a and a, comma c on both sides of a. Then limit x tends to a fx equals to L with a number L if and only if for every epsilon greater than 0 there exists delta greater than 0 such that 0 mod of x minus 1 greater than 0 less than a delta implies that mod of fx minus L less than epsilon. So we can explain this definition by this way. Whenever x goes to deleted neighborhood of a, then values of function lies in the neighborhood of L. That is, fx as x goes to closer to a from both sides but not equal to a, then fx goes to L. So whenever this happens, we say that fx tends to L as x tends to a. This is the formal definition of a limit. We can understand it by the graph also. Look here, if we have seen that we are looking here that x is goes to x as x tends to a from any sides of a, then values of function, this is y equals to graph of fx, so this value of function lies in the L plus epsilon, L minus epsilon for any epsilon, so for any epsilon we have a delta, so that the value of fx lies in the neighborhood of L. So this is the graphical definition of the formal definition of limit. So again we are moving on next situation, that what is the meaning of these definitions. So first of all we are explaining that what is meant by this. Mod of fx minus L less than epsilon means fx is arbitrarily close to L. This means fx is arbitrarily close to L. So we can make fx arbitrarily close to L by choosing epsilon. So again for arbitrary epsilon greater than 0, again what is meant by the 0 mod x minus a less than delta, that is, this implies that x lies in the deleted neighborhood of a. What is meant by deleted neighborhood of a? In deleted neighborhood of a, we mean that we exclude the value, the value of a does not exclude it. This means that x belongs to a minus delta, a plus a union a to a plus delta. So value of x lies in the deleted neighborhood of a, and this means that for all x not equal to a, x is sufficiently, if x is sufficiently close to a, for some delta greater than 0. So this, the definition of this limit says that the definition of the limit, formal definition of the limit tells that if x is not equal to a, if x is sufficiently close to a, then fx can be made to arbitrarily close to L. Then we say fx can be made to arbitrarily close to L when x is sufficiently close to a. So this is the formal definition of limit. then we say that limit exists. Again we are going to discuss an example to understand this definition. And what is example? Example is, we have to show that limit x tends to 0, x sine 1 upon x equals to 0. Note that this formal definition of limit is used in proving the limit. So again we have to prove that limit x tends to 0, x 1 upon x sine 1 upon x equals to 0. So let we choose any arbitrary epsilon greater than 0. So let epsilon greater than 0 be given. We need to find delta greater than 0 such that mod of fx minus L less than epsilon whenever x minus a less than delta. And what is a here? A equals to 0 and fx is x sine 1 upon x and L equals to 0. So mod of fx minus 0 equals to x sine 1 upon x minus 0. So this can be written as mod of x sine 1 upon x, and this can be written as mod x sine 1 upon x mod under the mod. Again we know that the value of sine is oscillatory between 1 and minus 1. So mod of sine 1 upon x lies between mod of less than or equals to 1. So mod of x sine 1 upon x minus 0 equals to mod of x sine 1 upon x is less than or equals to mod x. Again if this is less than epsilon, if we have taken this epsilon less than epsilon, then for delta equal to epsilon, mod of x minus 0 is less than delta implies mod of x sine 1 upon x minus 0 is less than epsilon. So what we have shown that 0 mod of x minus 0 less than delta, this delta equals to, for delta equals to epsilon greater than 0, we have shown that x sine 1 upon x minus 0 is less than epsilon. So limit x tends to, so we have shown that if x goes arbitrarily close to 0, then the function value of function lies in the neighborhood of 0. So if x tends to 0, x sine 1 upon x is arbitrarily close to 0, so the value of limit is 0. Thus we have proved that limit x tends to 0. Thus we have shown that limit x tends to 0 equals to 0. Again we are going to discuss another example. The second example is we have second example. The example number 2 is limit. We have shown that you have to show that limit x tends to 1, x plus 1 equals to 2. So For x tends to 1, we have to write 0 greater than mod of x minus 1 less than delta. So we have to find delta, such delta. So what we do, if fx equals to fx minus 2 equals to fx minus 2 equals to mod of x plus 1 minus 2 equals to mod of x minus 1. So if fx minus 2 less than epsilon for any epsilon, so this becomes mod of x minus 1 less than epsilon. So if we take delta equal to epsilon, if we take delta equal to epsilon, if we take delta equal to epsilon, what we get? We get 0 greater than mod of x minus 1 less than delta implies mod of fx minus 2 is less than epsilon. So we have proved that limit x tends to 1 fx equals to 2. So we have discussed two examples and the formal definition of the limit here. So thank you.